The Hubble Space Telescope recently captured a fascinating phenomenon: vivid blue jets of matter slicing through a nebula located 450 light-years away. This spectacle reveals the formation of a new star, FS Tau b, which is carving its path through a pancake-like cocoon of gas and dust. We can catch a glimpse of its faint glow, generated by the thermal energy as the cocoon contracts around it. In time, FS Tau b will reach a critical point, igniting nuclear fusion and shining brightly in its nebula, much like its neighboring star, FS Tau a, seen at the center of the photo. According to scientists, witnessing a star's birth is an extraordinary stroke of luck. For space explorers, this discovery sparks excitement and dreams of observing more celestial nurseries. But how exactly can we locate these cosmic cradles? And how many newly formed stars could we marvel at each year? Let's dive into these mysteries with astronomers as we chart our journey through the cosmos. So, where and how do stars come to life? Imagine the universe as a vast shadowy ocean filled with swirling clouds of gas, cosmic whirlpools that cradle the essential ingredients for star formation. These nebula, known as molecular clouds, are primarily composed of hydrogen, the simplest and most abundant element in the cosmos. In these clouds, hydrogen atoms bond together, forming molecules. However, these clouds are far from uniform. Different regions vary in density, temperature, and speed, creating ideal conditions for star formation in certain areas. Within these clouds, gravity gradually pulls matter together, creating dense clumps known as gas knots. Over time, these clumps grow in size, drawing in more material and eventually forming a protostar, a celestial body that emits heat yet has not achieved the mass necessary for nuclear fusion. As the protostar continues to accumulate mass, the pressure and temperature within its core escalate to extreme levels until nuclear fusion finally ignites. At this fiery moment, every atom within the core is set into a frenzied motion, colliding and fusing, which releases an intense burst of energy in the form of light. A new star is born, breaking the darkness with its brilliant glow. Star formation began around 155 million years after the Big Bang, and this process has carried on over 13.5 billion years, continually shaping the universe. Although the principles remain the same, star formation has evolved throughout cosmic history, allowing us to witness the birth of stars like FS Tau b across space and time. How did it all begin? Astronomers describe the early universe as mysterious and reluctant to share the secrets of its origins. However, with the powerful infrared tools of the James Webb Space Telescope and other advanced observatories, scientists have managed to catch glimpses of the universe's early light. Additionally, they build simulations of ancient cosmic regions, effectively rewinding the clock to unlock secrets of the universe's star-forming era. Researchers have discovered that modern stars differ significantly from their ancient counterparts, primarily in composition. While the amount of material matters, the degree of metal enrichment is also crucial. Astronomers categorize all elements heavier than hydrogen and helium as metals, which are created within stars through nuclear fusion. When stars explode as supernovae or shed layers during their red giant phase, they release these metals into space, enriching new clouds that will eventually form new stars. Thus, modern stars are cosmically distinct in their DNA from their ancient predecessors. So, what was the genetic code of these primordial stars? To explore this, an international team of scientists developed a simulation of early star formation. The results revealed that the first-generation stars were truly enormous, sometimes tens or even of times the size of our Sun, and they emitted incredibly intense light. However, they had very short lives, burning out in under 1 million years before erupting as supernovae and seeding the cosmos with heavy elements. Searching for remnants of these ancient stars might sound fascinating, but so far, astronomers have found no direct traces. However, a promising lead has emerged. The outer region of the Milky Way has been found to possess properties reminiscent of the early universe. It appears to be producing massive stars similar to those formed in ancient cosmic times. This area may contain remnants of prehistoric stars, although more research is needed. Interestingly, while the universe now has frequent star formation, only a tiny fraction of stars, around 1% were born in the first 650 million years after the Big Bang. The increased presence of elements heavier than hydrogen and helium eventually made it easier for gas clouds to condense, accelerating star formation across the cosmos. Today's stars vary greatly in brightness, size, color, and behavior. While some stars change over time, like transitioning from yellow dwarfs to red giants, others remain stable for trillions of years. Stars engaged in hydrogen and helium fusion are classified as main sequence stars, making up roughly 90% of the stars in the universe, with masses ranging from 1/10 to 200 times that of the Sun, and lifespans spanning millions to billions of years. If we spot a striking blue light in the sky, we're likely witnessing a rare blue giant, a young, massive star about 1,000 times the Sun's mass. Blue giants shine thousands to tens of thousands of times brighter than our Sun, but this brilliance comes at the cost of a brief 10 million year lifespan, making them extremely rare. Only about 0.1% of stars born in the universe are blue giants or hypergiants. Nevertheless, astronomers have identified enough of these exotic stars for us to explore. One of the most stunning blue stars lies 1,260 light-years away in the eastern part of Orion's belt, Alnitak, a triple star system. Its largest component is a blue supergiant, 28 times more massive and 20 times wider than the Sun, with a surface temperature of 28,700 degrees Celsius, 5 times hotter than our Sun. Alnitak is one of the brightest stars in the night sky, shining with a luminosity 31,600 times that of the Sun. Yellow dwarfs, like our Sun, may not shine as brightly as blue giants, but they emit a steady and robust light. In fact, these stars are relatively common, making up around 7% of all stars in the Milky Way. Due to their slow rotation, yellow dwarfs maintain almost perfect spherical shapes. Our Sun, for instance, has a radius of 695,700 kilometers, yet its polar and equatorial diameters differ by just 10 kilometers, marking it as one of the most perfect spheres in the universe. Despite its moderate pace, the Sun is far from idle. This main sequence star transforms hydrogen into helium at an astonishing rate of 600 million tons per second, converting around 4 million tons of matter into energy every second. This process releases about 30 billion times more energy than all the power plants on Earth combined. Other notable yellow dwarfs, such as 51 Pegasi and Alpha Centauri A, are similar powerhouses. Alpha Centauri, located a mere 4.37 light-years from Earth, is particularly intriguing. Once thought to be a single star, it was later revealed to be a binary system, with Alpha Centauri and B orbiting one another at a distance of just 40 to 47 astronomical units, cosmically close. Alpha Centauri A, shining with yellow light, is 1.5 times brighter than our Sun, while its orange counterpart, Alpha Centauri B, is slightly less massive but shines twice as bright. These stars, around 5 to 6 billion years old, are older than our 4 to 5 billion year old Sun and still have potential to form planets in their remaining lifespan of up to 10 billion years. Despite being called dwarfs, these stars are actually of average size. Interestingly, while they appear yellow due to Earth's atmosphere, yellow dwarfs are actually white-hot spheres. Red dwarfs, despite their name, appear more orange than red. These small stars have masses up to 1/3 that of the Sun and dominate the galaxy, making up 3/4 of all stars. Though small and relatively cool, red dwarfs have an extraordinary capacity for longevity. As they fuse hydrogen into helium, a natural mixing process pulls fresh hydrogen from their surface, providing a near-endless fuel supply. This unique cycle enables red dwarfs to burn steadily for trillions of years without changing their core structure. Remarkably, one of these stars, Proxima Centauri, is our closest stellar neighbor, just over 4 light-years away in the constellation Centaurus. This tiny red dwarf, the third component of the Alpha Centauri system, lies far from its companions at 13,000 astronomical units. Proxima Centauri is petite, with only 12% of the Sun's mass and a radius 7 times smaller. Its surface temperature is just above 3,000 Kelvin, and its luminosity is a mere 0.017% of the Sun's, making it invisible to the naked eye despite its proximity. Occasionally, Proxima flares due to magnetic activity, briefly increasing its brightness, though it still remains faint. In about 26,700 years, Proxima Centauri will move even closer, within just 3 light-years of the Sun. Using a home telescope, you can observe red dwarfs like Lacaille 8760 in Microscopium, or Lalande 21185 in Ursa Major, both visible from Earth. But what if we turn our gaze towards stars even dimmer and smaller than red dwarfs? Enter the realm of brown dwarfs, often called failed stars. These objects have masses between 13 and 80 times that of Jupiter, making them more massive than planets, but not quite stars. They emit very little visible light, yet scientists detect many brown dwarfs in the infrared spectrum. Brown dwarfs hold special interest because they form in a way similar to main sequence stars, emerging from gas and dust clusters within nebulae, though they lack the mass to initiate nuclear fusion. Some brown dwarfs may even form like planets within disks of gas and dust around stars. There's a theory that Jupiter in our own solar system might have become a brown dwarf if it had accumulated just a bit more mass, which would have made our system a binary star system. But instead, we have only the Sun, whose energy alone sustains life on Earth. A remarkable example of a young brown dwarf is LSRJ 1835 plus 3259, located in the constellation Lyra, about 20 light-years away. Although ultra-dim and ultra-cool, this brown dwarf is a fascinating target for astronomers, especially since brown dwarfs can create auroras, polar lights, 1,000,000 times more intense than those on Earth. Yet brown dwarfs are just one class among the multitude of stars filling our universe. How many stars exist in the vast cosmos? When we gaze at the night sky, it's easy to feel overwhelmed by the sheer number of stars. Imagine the challenge faced by early astronomers who tried to count them. Even under the clearest skies, only about 6,000 stars are visible to the human eye. While this may seem substantial, it's merely a fraction of the stars out there. Most lie far beyond our view. The Sun, our closest star, sits 150 million kilometers away. To estimate the total number of stars in the universe, astronomers first counted galaxies. They analyzed highly detailed images of small sky sections and counted each visible galaxy, finding that a single NASA image revealed about 15,000 galaxies as small dots and smudges. By expanding these counts, they estimated the universe holds around 2 trillion galaxies. While it's impossible to tally the exact number of stars in each galaxy, scientists have found a way to approximate this number. In our own Milky Way, which holds a mix of red, white, orange, and blue stars of various sizes, astronomers counted roughly 100 billion stars by measuring the light emitted across the galaxy. Multiplying this figure by the number of galaxies leads to a staggering estimate, approximately 200 sextillion stars, 200 billion trillion. Imagine this. The sheer magnitude of this number is nearly impossible to grasp. It's like imagining a quantity about 10 times greater than the number of water glasses that could be filled from all the oceans on Earth combined. The universe, filled with stars and galaxies, is a dynamic, ever-changing canvas. Stars aren't just dazzling points of light, they are the essential building blocks of the cosmos. Think of galaxies as bustling cities, with stars as the lively shops, homes, and venues that make these places vibrant. A young galaxy is like a newly founded town, with only a few stars scattered like empty lots and silent streets. But as stars begin to form, these galactic towns come alive, transforming into bright, bustling metropolises lit by young, energetic stars that infuse warmth and activity into the vast reaches of space. The gravitational forces of stars shape remarkable formations, like the spiral arms of galaxies. New stars are born each day, illuminating these cosmic cities with fresh light. Yet, as some stars emerge, others reach the end of their lives and fade away. How frequently do these stellar births and deaths occur? Scientists, using well-tested methods, have approximated these rates. In our own Milky Way, about 7 new stars form every year, drawing material equivalent to roughly 4 solar masses. In the same galaxy, about 2 massive stars explode as supernova each century. Thus, the birth rate of stars slightly surpasses the death rate, though precise tracking is complicated by gas and dust obscuring much of the galaxy. Across the broader universe, star formation rates differ significantly. Large elliptical galaxies produce nearly no new stars, whereas star-forming nurseries are abundant in spiral galaxies. Some galaxies generate stars at rates 100 to 1,000 times higher than the Milky Way. By averaging star formation rates across different types of galaxies, scientists estimate that over 150 billion new stars are born annually throughout the universe. Many of the cosmos's star factories are found in nebula and molecular clouds. One of the most active is the Orion Nebula, located 1,300 to 1,600 light-years from Earth. This nebula teems with young stars, glowing amidst thick clouds of gas and dust. The density of matter within the nebula fosters star formation, and the radiant glow from newborn stars illuminates the entire region, visible even to the naked eye. A small telescope reveals the nebula's captivating features: swirling dust, explosions, and beams of starlight breaking through dense clouds. The Orion Nebula's beauty stems from natural forces, painting the nebula with shades of blue and violet from hot stars, green from ionized oxygen, and red from hydrogen. Yet, the same stars that illuminate it also contribute to its eventual dispersal. Intense stellar radiation has already stripped away much of the nebula's mass over the past 400,000 years. Eventually, it will exhaust its star-forming materials, leaving behind only a sparse star cluster. But for now, the Orion Nebula remains an astronomer's paradise, offering breathtaking views of the universe in action. A recent fascinating discovery has emerged in the Orion Nebula, capturing astronomers' attention. The James Webb Space Telescope unveiled peculiar fingers of gas in Orion, an extraordinary formation that resulted from a stellar collision between two massive young stars around 500 to 1,000 years ago. These cosmic fingers radiate a red glow from hydrogen heated by the explosion, turning green near the tips due to the presence of iron atoms, and glowing white in the hottest regions. Yet perhaps the most breathtaking sight in the cosmos is the Pillars of Creation in the Eagle Nebula, a powerful testament to the universe's endless beauty and potential. When the Hubble Space Telescope first captured this image in 1995, it mesmerized millions, symbolizing the marvels of space. Approaching the pillars, we encounter towering columns of gas and dust, sculpted by natural forces but resembling grand celestial sculptures. Illuminated by the intense ultraviolet light of nearby young stars, the pillars contain hidden stars forming within dense whorls of gas and dust. The Tarantula Nebula, the universe's largest known stellar nursery, is located in the Large Magellanic Cloud about 170,000 light-years away. Spanning an immense 1,800 light-years, this nebula houses around 800,000 stars, including some massive monster stars. The largest of these, R136A1, is about 196 times the mass of our Sun. These giant stars drive powerful winds that carve interstellar gas and dust into magnificent bubbles. Some stars have already exploded as supernovae, lighting up these bubbles with X-rays. At the heart of the nebula, where three bubbles converge, lies a dense cluster of young stars only around 2 million years old. Surrounding the edges are newly forming star clusters and globular clusters, with many more stars anticipated to emerge. In 2022, the James Webb Space Telescope observed thousands of almost newborn stars within the depths of the Tarantula. Another striking region, the Witch Head Nebula in the constellation Eridanus, is 800 light-years away. Its eerie, witch-like profile glows softly with reflected light from Rigel, one of the brightest stars in our sky, casting a blue tint due to Rigel's blue light emissions. Yet, despite its appearance, the Witch Head Nebula is anything but sinister. It is actively generating new stars, with around 20 protostars preparing to join the celestial landscape. Spiral galaxies as star factories. Many galaxies, including our own Milky Way, produce stars at astonishing rates. The Milky Way, a prominent spiral galaxy, serves as a model for understanding star formation across the universe. Its structure is a stunning spiral, a flat, blue-white disk of stars, gas, and dust, with a bright yellowish bulge at the center, connected by a bar of intense star formation. The spiral arms of the Milky Way extend from this central bar rather than from the bulge, drawing gas toward the core along these majestic arms. Over recent years, astronomers have focused on key star-forming regions within the Milky Way, particularly those near the Sun and within the galactic disk, enhancing our understanding of how stars are born within spiral galaxies. Elliptical galaxies account for nearly a third of all observed galaxies, displaying a surprising variety in shapes, from nearly spherical to elongated, cigar-like forms. Although their appearances may differ, elliptical galaxies share a common trait. They are older and contain minimal gas and dust, which makes new star formation rare. Instead, they mostly house cool, red stars such as red giants. Unlike spiral galaxies, where stars orbit in an organized disk, stars in elliptical galaxies move around their centers in random paths. The masses of these galaxies vary greatly, ranging from millions to hundreds of billions of solar masses. However, not all elliptical galaxies fit the profile of quiet elders. In the constellation Sextans, about 12 billion light-years away, lies an elliptical galaxy experiencing a cosmic baby boom. Unlike typical ellipticals, this galaxy is remarkably productive, forming a new star every 2 hours, equivalent to 4,000 stars per year. At this rate, it could become one of the most massive galaxies ever observed within just 50 million years, earning its nickname as a true star factory. In addition to ellipticals, we find irregular galaxies, some of the universe's earliest formations lacking any defined shape. These amorphous galaxies may seem inactive at first glance, but they are actually thriving hubs of star formation. Rich in gas and dust, irregular galaxies provide ideal environments for new stars to form. One notable example is NGC 1569, a dwarf irregular galaxy in the constellation Camelopardalis, located between 7.8 and 11 million light-years away. Though this dim, fuzzy object often goes unnoticed by astrophotographers, closer examination reveals an incredible glow filled with young stars, including massive Wolf-Rayet stars under 5 million years old. As we journey further, we encounter regions packed with intense star-forming activity. These areas are abundant in gas and dust, which supply the essential materials for new stars, unlike regions where these elements are scarce and star formation is minimal. However, star formation depends on more than just raw materials. Other factors, such as local temperature, rotational speed, and proximity to neighboring objects, all play critical roles in determining the level of star-forming activity in a given area. One of the universe's enduring mysteries is the sudden increase in star formation seen in some nebulae and galaxies. Scientists suggest that these starbursts could be triggered by various cosmic events. For instance, the galaxy M82 began an intense period of star formation after passing close to its neighbor, M81. This encounter left a stream of neutral hydrogen connecting the two galaxies, suggesting that M82 may have acquired new material from its companion. This influx of matter resulted in numerous supernova remnants, evidence that star formation has been vigorous there for millions of years. Encounters between galaxies often have dramatic outcomes, and in some cases, they can lead to violent interactions that alter the galaxy's structures and star-forming activities. Galactic collisions are monumental events. Despite the vast expanse of space, galaxies often cannot avoid each other, leading to inevitable encounters. When they do meet, however, there are no crackling sparks or explosive scenes. Instead, galaxies glide through each other almost undisturbed, with their stars remaining unscathed due to the immense distances between them. But in the wake of their meeting, gas clouds from one galaxy do collide with those of the other. These impacts compress the gas, triggering waves of new star formation. Meanwhile, the gravity of both galaxies generates massive ripples, distorting their shapes into intriguing forms, ghostly bars, rings, and immense tidal tails teeming with young stars. One extraordinary example of this process is seen in the antennae galaxies of the NGC 4038 group. Named for their long, antenna-like tails, this pair of spiral galaxies began interacting hundreds of millions of years ago. The collision stirred up spiraling patterns of gas and dust and ignited intense star formation, filling these galaxies with billions of newly born stars. In images, nearly half the faint spots are young clusters, each containing tens of thousands of stars. The galactic cores, seen as orange patches, are primarily old stars interlaced with dark dust filaments, while the bright blue areas mark regions of active star formation, surrounded by pinkish hydrogen gas. But galactic collisions sometimes lead to more than a burst of new stars. Recently, astronomers uncovered another dramatic consequence. Supermassive black holes in merging galaxies can consume entire star systems. This devouring process usually ends with a spectacular burp, ejecting vast amounts of matter into space as radiation that can be detected millions of light years away. Such events are common in galaxies that have experienced rapid star formation over the past few billion years, a pattern often triggered by galaxy mergers. These galactic car crashes funnel stars toward the supermassive black hole at the galactic center. Additionally, black holes from each galaxy can orbit each other, forming a dual system that consumes stars even more voraciously than a single black hole. Scientists believe the Milky Way will eventually collide with the Andromeda Galaxy in about 4 billion years, possibly sparking a similar scenario. It's conceivable that our solar system could be nudged towards Sagittarius A*, the Milky Way's supermassive black hole. Although this scenario sounds daunting, the Sun's current distance of 27,000 light-years from the galactic center lowers the risk of direct involvement. Observations show that black holes tend to devour star systems closer to the galactic core, rather than those in the outer regions. Supernovae also play a critical role in cosmic evolution. When these massive explosions occur, they obliterate everything nearby, yet they also act as star creators by dispersing enriched material. The expelled matter forms clouds rich in metals and other elements, seeding the formation of new stars. While this process is still not fully understood, scientists hope to learn more by observing supernovae as they unfold in real time. One star long suspected of an impending dramatic fate is Betelgeuse, the red giant in Orion. In 2022, it sparked a social media frenzy with rumors that it might go supernova within months. Some enthusiasts prepared for a once-in-a-lifetime spectacle, while others worried it might impact Earth. However, astronomers assure us that such an explosion would have minimal effect on our planet, given Betelgeuse's distance of 700 light-years. Nonetheless, Betelgeuse remains an unpredictable star, occasionally surprising observers with bright outbursts before settling back into its usual luminosity. Scientists acknowledge that with such a variable star, surprises are always possible. Yet, there's another star, Tau Corona Borealis, with an even higher chance of delivering a spectacular show soon. Positioned 900 light-years away, this star is predicted to become a recurrent nova, with NASA estimating it could flare up within the next 2 months, possibly as early as September. Typically, supernova predictions are challenging, but recurrent novae are more predictable due to their regular explosive cycles. Tau Corona Borealis, for example, erupts approximately every 79 years, much like Halley's Comet's 75 to 80-year cycle. Its last eruption occurred in 1946, so another is imminent. How is NASA able to pinpoint this timing so accurately? Observations and detailed calculations provide the clues. A star nearing nova generally dims about a year beforehand, and Tau Corona Borealis has been fading for nearly 10 months. NASA's experts not only anticipate when this explosion will happen, but also understand why. This binary star system consists of a white dwarf and a red giant, each orbiting a shared center of mass. White dwarfs are incredibly dense objects, packing a mass similar to the Sun's into a body the size of Earth. This high density and intense gravity allow the white dwarf to capture material ejected by its red giant companion, gathering it layer by layer on its surface. Over years, as the dwarf reaches its density threshold, a thermonuclear reaction ignites, similar to a warhead's detonation, expelling accumulated material in a bright eruption visible from Earth. For a short time, this eruption causes the white dwarf to shine far more brilliantly than its larger companion, increasing the system's brightness by a factor of thousands or even hundreds of thousands. This time, NASA anticipates that Tau Corona Borealis could match the brightness of Polaris, the North Star. The explosion should be visible to the naked eye for several days, potentially even lasting over a week. After releasing its accumulated material, Tau Corona Borealis will quiet down for several decades until the process begins anew. This upcoming event promises a spectacular show, perfect for astrophotography enthusiasts hoping to capture rare and stunning images. Scientists also see it as an opportunity to learn more about mass exchange in binary systems, better understanding nova explosions, and observing a white dwarf's transformation into a nova. The aftermath could even ignite a fresh burst of star formation within the system. Astronomers will be watching closely, hoping to shed light on the elusive processes of stellar evolution. Stars often guard their secrets, revealing the mysteries of their origins and lives only gradually. One enduring question is why star formation continues today. Why hasn't all the cosmic gas ignited in an endless blaze of starlight? Each answer seems to uncover more mysteries. For instance, Polaris, a Cepheid variable, has recently shown a shift in its pulsation period, which used to last 4 days but is now shorter with a higher amplitude. This change may be caused by gravitational interactions with a nearby star, possibly stirring up outer layers that expel material into space, forming the seeds of a future star. Though we may not witness this star's birth, we can imagine the universe's miraculous processes in motion. Somewhere in the vast cosmos, within trillions of galaxies, a new star is emerging from its cosmic cradle. Observe this image. It's a remarkable photo captured by a $10 billion marvel of engineering, the James Webb Space Telescope, stationed 1.5 million kilometers from Earth. Scientists across the globe waited nearly 25 years to witness this view. At first glance, it may seem like just another image of space, but its significance rivals historic moments like humanity's first steps on the moon or Yuri Gagarin's inaugural journey beyond our atmosphere. So, what does this photo truly reveal? It shows a star nestled within our Milky Way galaxy, marking the James Webb Telescope's first successful capture after deployment. This confirms not only the full functionality of the telescope, but also its outstanding performance, surpassing all expectations. This photo represents a monumental leap, positioning humanity on the edge of new cosmic discoveries. With the Webb's capabilities designed to detect life-supporting conditions beyond Earth, it brings us closer than ever to answering the question, are we alone in the universe? Constructing the James Webb Telescope involved 25 years of work by thousands of engineers and scientists worldwide, with a $10 billion investment. But what do scientists hope to achieve with it? Consider the construction of the 27-kilometer Large Hadron Collider, completed over a decade with a similar budget, which led to the discovery of the Higgs boson. Online, you'll find countless articles and videos about this space telescope, perhaps already familiar with its infrared capabilities and sensitivity, 100 times that of the Hubble. Creating this precision required an intricate folding mirror of 18 hexagonal segments. Webb was launched on December 25, 2021, from the Kourou spaceport in French Guiana. As the Ariane 5 rocket disappeared into the clouds, thousands around the world held their breath, hoping for success. But the mission's suspense continued long after launch. This three-story telescope, with a surface area comparable to a 25-car parking lot, had to be deployed and made operational in space without human intervention. The telescope's success hinged not only on unfolding its sunshield and mirror, but also on aligning the 18 segments with nanometer precision, a tremendously complex task. In February, encouraging news arrived as the telescope systems successfully reached full operation. Shortly after, the first photograph, showing the star HD 84406 in the Ursa Major constellation, captivated the world. This star, selected to test the telescope's performance, sparked intense global interest despite its simplicity. Its isolation in the sky made it ideal for confirming James Webb Telescope's functionality, enabling precise calibration of each mirror segment. To ensure the near-infrared camera could capture and focus light, scientists spent nearly 25 hours gathering and processing 54 gigabytes of raw data, creating a mosaic that displayed the alignment of each segment. Following weeks of calibration, NASA announced the successful alignment of Webb's mirrors. This marked a critical milestone in the telescope's journey, represented by another unassuming star image with only a catalog number. This painstaking work has brought us one step closer to unprecedented discoveries that could forever change our understanding of the universe. Though 16 times brighter than the Sun, this star has no particularly distinctive features. Located 2,000 light-years away in our galaxy, it is just one of the 400 billion stars within the Milky Way. NASA's James Webb Space Telescope captured this star using a red filter to enhance its brightness. Unlike the deep cosmic visuals we often see from Hubble, this image focuses on clarity in the infrared spectrum, delivering the highest quality image ever taken in space. And what about the faint structures in the background? Those are distant stars and galaxies, adding a striking depth that makes this image iconic. Among these distant galaxies is one situated 5 billion light-years away, a remarkable feat considering Webb's mission is still in its initial testing phase. During its first trial, Webb focused on a star and detected an object 5 billion light-years away. NASA also released the telescope's first selfie, captured with the near-infrared camera, which showed the alignment of its 18 mirror segments. Over the coming months, these segments will be finely adjusted to work as a single, perfectly tuned mirror. Meanwhile, the James Webb Telescope was also photographed by the Gaia Space Telescope, both of which orbit around the Lagrange point, L2. On February 18th, Gaia captured Webb as a faint light spot from about 1 million kilometers away, visible thanks to Webb's reflective sunshield. These initial focused images are crucial, with breakthrough discoveries anticipated mid-year when the telescope operates at peak resolution and all scientific instruments collect data. So, what are NASA's goals for Webb's first year? James Webb's initial observations will include nearby dwarf galaxies, remnants of supernovae, and the universe's earliest stars. Serving as a kind of cosmic time machine, Webb will allow us to peer back 13.5 billion years, nearly reaching the origins of the universe, believed to have formed 13.8 billion years ago. The telescope may capture some of the most extraordinary cosmic events humanity has ever seen, such as the formation of the first galaxies and the universe's early structures. In one of its earliest historic captures, Webb imaged galaxy GN, Z13, the most distant and ancient galaxy observed so far, formed just 300 million years after the universe's inception. Since beginning its scientific mission in mid-July, Webb has already astonished scientists and space enthusiasts alike with its vivid imagery and groundbreaking discoveries. Prepare to explore how the telescope has detected exoplanets with possible life-supporting conditions, taken images covering an area equivalent to 1/5 of the Moon's diameter, and even revealed Jupiter's rings in unprecedented detail. The James Webb Space Telescope offers numerous advantages over the Hubble telescope. Positioned at about 1.5 million kilometers from Earth, 4 times farther than the Moon, it avoids the interference from Earth-orbiting satellites that can affect Hubble, which orbits only 547 kilometers above Earth. Unlike Hubble, which primarily captures visible and ultraviolet light, Webb is equipped with both near-infrared and mid-infrared cameras. Astrophysicist John Mather noted that Webb's sensitivity could detect something as small as a bumblebee at the distance between the Earth and Moon. Thanks to its infrared vision, Webb can peer to the universe's farthest reaches, where the oldest stars and galaxies reside. Hubble struggles to penetrate the dense clouds of gas and dust around many stars, planetary systems, and galaxies, but Webb's infrared capabilities allow it to see through these veils, akin to an X-ray. Webb's 6.5-meter diameter mirror, the largest ever sent into space, is nearly 3 times the size of Hubble's, capturing significantly more light. This powerful mirror allowed Webb to capture incredibly sharp, detailed images of the early universe in just a day, a task that would have taken Hubble weeks. In one of Webb's images, thousands of galaxies fill the frame, and at the center, a galaxy cluster, SMACS 0723, acts as a gravitational lens, bending light from more distant galaxies behind it, causing them to appear stretched and distorted. Some galaxies are so distant and faint that no telescope has ever imaged them before. Webb's first target in our solar system was Jupiter, observed during initial testing. These images revealed the gas giant's complex atmospheric bands and the iconic Great Red Spot in stunning clarity, exceeding astronomers' expectations. Following Jupiter, Webb turned to the exoplanet WASP 96b, a gas giant discovered in 2013, located about 150 light-years away in the Phoenix constellation. Although less massive than Jupiter, it is 1.2 times larger in diameter and orbits extremely close to its yellow dwarf star, heating to over 1,000 degrees Celsius. Webb detected clouds, haze, and traces of water in its atmosphere, marking a breakthrough that Hubble had taken decades to confirm. Webb's swift detection of these molecules thrilled astronomers, as it sets the stage for future discoveries of life-supporting elements like water, oxygen, carbon dioxide, and methane on rocky planets. In another captivating image, Webb captured the Southern Ring Nebula, NGC 3132, about 2,000 light-years away in the Vela constellation. A gas cloud encircles a dying star, not formed by the central star, but by a second star nearby. Over thousands of years, this star emitted at least 8 layers of gas and dust, while the bright central star stirred these layers, forming intricate rings within the nebula, much like sunlight streaming through clouds. Hubble had previously imaged NGC 3132, showing its colorful and complex structure, but Webb's image reveals even finer details, capturing not only the nebula itself, but also distant galaxies in the background. In Webb's images, bright stars show 6 diffraction spikes due to its segmented 18-hexagon mirror design, while Hubble's images feature 4 spikes, caused by its single round lens with a secondary mirror mounted on 4 supports. Take a look at this breathtaking image, a vast swirling purple vortex. This is Webb's view of the spiral galaxy NGC 628, situated in the constellation Pisces, about 32 million light-years from Earth. Unlike Hubble's images, Webb's infrared capabilities provide a unique perspective, highlighting the dust and gas that obscure much of the starlight, while revealing supernova remnants and star-forming regions that infuse the galaxy with life. This image captures the dynamism of these regions as stars peek through the cosmic dust. Now, observe this larger image from Webb, spanning approximately 1 arc-minute in diameter. It features Stephan's quintet, a tight cluster of galaxies in the constellation Pegasus, about 290 million light-years away. 4 of the 5 galaxies appear to be locked in a gravitational dance, moving closer and occasionally merging, while the 5th galaxy lies some 40 million light-years away, observing the spectacle from a distance. The image is both awe-inspiring and visually striking. On July 12, 2022, Webb captured the nebula NGC 3324 in the constellation Carina, a stunning star-forming region that appears like a celestial landscape of mountains and valleys twinkling with stars. Webb's sharper images bring out even more details than Hubble's previous views. Nebulae, composed of interstellar gas and dust, come in 3 forms: emission nebulae, reflecting starlight; reflection nebulae, scattering light; and dark nebulae, like the famous Horsehead Nebula, which remain unilluminated. Formed from supernova explosions that scatter stellar remnants, these nebulae act as star nurseries, where gas and dust coalesce under gravity, forming a dense sphere that eventually ignites as a star. On September 12, 2022, Webb released an image of the Orion Nebula, 1,300 light-years away in the constellation Orion, and visible even to the naked eye. Webb's photograph reveals the Orion Bar, a massive wall of gas and dust. 2 of the brightest stars, members of the trapezium cluster, formed here 300,000 years ago and emit intense ultraviolet light that sculpts and illuminates their surroundings. Another breathtaking image from Webb, shared by NASA on September 6, 2022, is the Tarantula Nebula, located 161,000 light-years away in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. As the largest and most active star-forming region in the local galaxy group, the Tarantula Nebula is home to exceptionally massive and hot stars, resembling ancient star-forming regions from the early universe. Webb's near-infrared camera revealed thousands of young stars previously obscured by dust, surpassing Hubble's abilities. At the center of the nebula lies a vast cavity encircled by radiant clusters of massive stars, casting a blue glow that accentuates the nebula's ethereal beauty. The Southern Ring Nebula, or NGC 3132, is a planetary nebula, so named because early astronomers mistakenly thought it resembled a planet. These nebulae are expansive clouds produced by giant stars nearing the end of their lives, shedding their outer layers as they become increasingly unstable. While planetary nebulae may seem rare, they're actually quite common. In our galaxy, which holds 200 to 400 billion stars, over 150 planetary nebulae have been documented. Situated about 2,500 light-years away in the constellation Vela, the Southern Ring Nebula has been observed in remarkable detail by the James Webb Telescope. Webb revealed that this nebula was formed by two stars in a binary system, rather than a single star. The brighter of the two stars influences the nebula's asymmetrical shape, while the central, aging star has already evolved into a white dwarf. The James Webb Space Telescope was designed to propel discoveries across various fields of astronomy, allowing scientists to delve deeper into the mysteries of star formation, galaxy evolution, and exoplanet characteristics. One of Webb's foremost missions is to capture light from the first galaxies that emerged after the Big Bang, providing insights into not only how galaxies form and evolve, but also into the broader story of the universe. Equipped to see in near and mid-infrared, Webb can peer into the early universe, observing ancient galaxies and cosmic structures that remain beyond Hubble's reach. Why the focus on the oldest galaxies? Observing them sheds light on the cosmic dawn, the epoch in the early universe when stars began to shine, illuminating the cosmos for the first time. It's like discovering a childhood photo of your great-grandmother. Thought to have begun 13.8 billion years ago with the Big Bang, the universe then entered a dark age, gradually cooling until matter clumped together under gravity. By studying these ancient galaxies, astronomers hope to answer foundational questions about our universe's origins. Already, Webb's images and data have challenged prior assumptions, reshaping our understanding of the earliest cosmic epochs. James Webb's data suggests that the universe's first galaxies appeared earlier than previously thought, and they seem more numerous and luminous than astronomers had anticipated. Surprisingly, these early galaxies display an orderliness and calmness that contrast with traditional models of chaotic early galaxy formation. Researchers theorize that dark matter halos likely provided a foundation for galaxy formation, attracting ordinary matter, like hydrogen gas, that condensed within them. Among these early galaxies, some are incredibly bright and ancient. For instance, the galaxy GSZ 130, one of the oldest known, formed around 320 million years post-Big Bang and is situated 13.6 billion light-years away. However, due to cosmic expansion, it is now around 33.6 billion light-years distant. These early galaxies were smaller than the Milky Way and produced stars at an astonishing rate, puzzling astronomers as to how they could form so many stars in such a short span. Some speculate they may contain an earlier, third-generation type of star that we have yet to observe or confirm. In a breathtaking November 2022 image, Webb captured the protostar L1527 in Taurus, with light shaped like celestial hourglasses. Dubbed the cosmic hourglass, this shape results from material propelled by the protostar, colliding with its surroundings and creating cavities. In the center, a horizontal accretion disk of gas and dust can be seen feeding material to the forming star. NASA suggests that this glimpse of L15527 offers clues about our Sun and Solar System's earliest stages. Though nuclear fusion has yet to commence in L15527, it will eventually accumulate mass, contracting and heating until fusion ignites and a new star is born. These snapshots offer just a preview of Webb's contributions, illustrating the depth and wonder of our cosmic origins. Many of Webb's findings validate long-standing theories, yet many questions about the universe's earliest stars and galaxies remain. The journey of discovery is only beginning, and we await the marvels that lie ahead. A little over 40 years ago, humanity sent 2 maps of Earth's location into space, which were attached to the exterior of 2 spacecraft. Now, both spacecraft are the farthest artificial objects from us. Today, the Voyager probes are located at the edge of the solar system, continuing their endless journey. If these probes ever encounter extraterrestrial intelligent civilizations and decipher the information on the plaques, it will not only reveal when the spacecraft left their home, but also point the way to our small and cozy world. It would be ideal if this civilization turns out to be peaceful and friendly. However, what if these sentient beings prove to be hostile? What if the potential Voyagers pose a threat to all life on Earth? Traditionally, people's opinions on this matter are divided into 2 camps. Some argue that it is extremely dangerous, and humanity should not have sent out such information, potentially exposing us to unknown risks. Others believe that the chances of encountering hostile beings are slim, and the scientific and cultural value of potential communication outweighs the risks. There is also a third category of people who do not share the opinions of either the first or the second group because they simply don't care. They are indifferent to the whole discussion. However, it's boring and uninteresting to talk about them, so let's focus on the first 2 opposing opinions and examine each of them in more detail. But before that, it would be good to understand what this map actually is, located on board Voyager. It's not the kind of map we are accustomed to, with north, south, west, and east as familiar markers. Instead, pulsars are used as markers. Pulsars are essentially rapidly rotating stellar remnants. They have existed for many millions of years, and each pulsar has its unique pulsation or flickering pattern, which can be used to calculate the position of objects in their vicinity. The famous astronomer Frank Drake, along with the equally famous scientist and writer Carl Sagan and the rest of the team, prepared golden records. These records were created by Drake and contained cosmic landmarks. These golden records, placed on Voyager's spacecraft, indicated the location of Earth in both spatial and temporal coordinates. But let's go back to pulsars. Why were they chosen, and why will extraterrestrial civilizations be able to decipher the coordinates of our world correctly because of them? Earthly time measurement would be meaningless because it is based on the rotation of our planet around the Sun. Another complication arose with the spatial coordinate system in space. No one will find us based on directions like up, down, east, or west. Even the stars change their astronomical timescale over time. An explanation like the second star to the right, then to the left, and straight until morning won't help those who may discover the probes, say, 1 billion years later. By the time the message reaches its recipient, such as the star Betelgeuse, which could serve as a coordinate point, it may no longer exist. That's why pulsars, discovered in 1967, were chosen. These super-dense dead stars act as excellent beacons in both spatial and temporal coordinate systems. They have very long life cycles that can last from tens of millions to possibly billions of years. Each pulsar is unique, and they rotate incredibly fast and emit pulses of electromagnetic radiation, which makes their behavior similar to that of a lighthouse. By calculating the delay between these pulses, astronomers can determine their rotation speed with incredible accuracy. Over time, the speed of pulsars slows down, sometimes by billionths of a second per year. By comparing the current rotation speed of a pulsar with the speed indicated on the discovered map, intelligent life could determine how much time has passed since the map was created. Drake hypothesized that if these beings can understand what pulsars are, they would definitely know their location in the galaxy. Using the obtained map, they could approximate the launch time of the spacecraft and trace its trajectory, ultimately leading them to the Sun. At that time, there wasn't much debate about the pros and cons of contact with extraterrestrial intelligence. Why? Because when Voyager 1, which is essentially Voyager 2, was launched, scientists had no idea if there were other planets beyond the solar system. It was all speculation. Therefore, no one really speculated about the possibility of intelligent life elsewhere. However, just over 10 years later, the Hubble Space Telescope appeared, and we now know that planets are quite common in our galaxy. The percentage of intelligent life on these worlds may be similar to our Earth. This revelation has sparked a strong desire to send targeted radio messages towards promising star systems. Among scientists, other prominent individuals, and especially our viewers, debates have intensified about whether our decision was wise and whether it would be better to simply continue listening to the cosmos rather than striving to be heard. However, for Voyager, it is already predetermined. They are there, they are flying, carrying a map of our home, and if someone is out there, they will definitely be able to find us. Therefore, we can only talk about the majors in hindsight. We cannot bring them back, and we cannot catch up to them. And why did we get fixated on Voyager? There are also Pioneer 10, Pioneer 11, and the New Horizons spacecraft, all carrying messages for extraterrestrial civilizations. If we rephrase the question and formulate it as whether it is worth sending signals with information about Earth into space, it raises more food for thought about the essence of it all. Let's ponder if it is dangerous or not. For example, the late Professor Stephen Hawking warned back in 2010 that humans should remain as quiet as possible because otherwise, advanced aliens interested in Earth's resources could take over the planet. He likened the situation to Columbus's landing in America, which did not turn out well for the Native Americans. To some extent, this is true. However, Dr. Douglas Vakoch from the SETI Institute in California has a different perspective, as this is precisely the institute dedicated to the search for extraterrestrial intelligence. Some believe that we should refrain from powerful transmissions, fearing an alien invasion. If these views spread, humanity would become isolated, avoid exploration, and minimize risks at all costs. Well, that's also true, isn't it? But can we not send signals directed at any stars or exoplanets? Not sending them into space is not possible because our planet has a constantly expanding, easily detectable radiosphere. It carries information about our civilization, such as the radio signals generated by television, cell phones, and satellites. Their presence can be easily detected from space, even though radio signals weaken the farther they are from their source. The entire question lies in their detection, which depends on the characteristics of the receiving equipment. Ordinary radio broadcasts can be detected if someone is actively searching for them, and hostile civilizations eager to attack someone will easily determine the location of Earth and the presence of life on it. Or, let's assume that extraterrestrial civilizations exist nearby. Let's take a look at ourselves from their perspective and try to answer the question, are we interesting to them? To answer the question of whether we are interesting to them, we occupy all our free time with blatant brawls. Historians once created a remarkable graph in a logarithmic scale, with time on the axes, starting from 6,000 years ago when the first writing appeared, and up to our time. They measured the duration of wars for each year, and it turned out that in the entire span of 6,000 years, there were only 3 months of peace when there was no war on the planet. A civilization engaged in self-destruction is not of interest to anyone, except perhaps to observe from a distance without making contact, just as we do when we observe fighting beetles in a jar. Or let's say that for an extraterrestrial civilization, their intentions are indeed aggressive, confirming the fears of Stephen Hawking and others. Why would they come here to engage in warfare and expend energy and resources? What valuable resources does Earth possess? It is unlikely that they would come here for oil, water, or anything else. Perhaps we humans ourselves are the valuable resource. But enslaving us for hard labor doesn't make sense. It's not beneficial at all. Humans are susceptible to illness, fatigue, and need food and drink. Moreover, they are fragile and cannot work for extended periods. If a civilization is truly intelligent, it would be easier for them to build an army of robots to handle laborious tasks. But in reality, if there were many such civilizations, whether good or evil, it wouldn't matter. This means that they haven't developed such ships and won't come, and we will never travel anywhere. It's all due to the tremendously vast scales of space. For example, we received a signal from a civilization living at the center of our galaxy. The signal from their council takes 30,000 years to reach us. We urgently send them a response, requesting knowledge about the universe, equations of quantum gravity to be placed in their library, and everything else. But even if they receive the signal, it will take another 30,000 years for their response to reach us. So for those who receive it, it becomes pointless. And if we consider intergalactic distances, the Andromeda Galaxy, the closest one, is 2 million light-years away. This means we will receive that knowledge in 4 million years. Let's assume that in a galaxy with 100 million stars, there are millions of civilizations similar to ours. But some of them emerged 100 million years before us, while others will emerge 100 million years later. What would we even talk about with civilizations that are 100 million years older than us? We would be like insects or microbes to them. Let's say we send them a signal, they receive it, and from their perspective, they see it as something trivial. In conclusion, the likelihood of the maps on board the Voyagers reaching the shores of extraterrestrial civilizations is extremely low. The spacecraft are not aimed at any specific star. They are simply flying. If extraterrestrial civilizations have powerful enough radars, they might be able to detect Voyager from afar. But in that case, they would have already detected signals from our planet, according to our channel's opinion. The Voyager spacecraft, just like the Pioneers and New Horizons, pose no danger to Earth. Instead, they are a reason for pride. Imagine that those images, sounds, and maps of planet Earth can endlessly and imperceptibly float through space. Moreover, they will likely outlast us. Humanity might not exist, but at some beautiful moment, these artifacts made by human hands could be the last remnants in the universe.